And for this one here, what we want to do is we want to find the point that is on this line that is closest to this one here. So it's kind of like this. Let me just tilt the paper like this. I need a point that is somewhere on this line such that if I stop, then the distance between that point and here is minimized. So it's not going to be there because if you look at that distance, I can get closer to this point than here. If I just move along slowly here along this line, that's a little closer. It turns out that the point on this line that works is going to be the point that if you connect it to 74, 0, it creates a perpendicular angle, a perpendicular intersection, right? The lines are perpendicular. And you've heard this often, like in everyday life and in the movies. You hear people say that, the shortest distance between 2 points is a straight line, but not just a straight line, but a direct line, the perpendicular line. So here, this point is called point P, and point P has coordinates x, y. These are the coordinates of point P. And for the first part, they want us to create the objective function in terms of x. So the distance formula. Recall that the distance formula has this template right here, where what we do for the distance formula is we subtract the x's and then you subtract the y's in any order. For instance, in here, let's go x minus 74. And then in here, let's go y minus 0. But in the directions, they wanted only the variable x to be used. But that's all good because we know what y can turn into. Because note that y, this y coordinate, y is the same as 6x. So really, the coordinates of point P are x, 6x. And that's good because instead of y, you can write 6x minus 0 like that. So now let's just clean this up a little bit. So I expanded that binomial to get that. That squared is just that. Now let's actually add these together. So I combined 1 with 36 to get 37x squared. And then we have these pieces here. Now, as it turns out, 37 actually goes into all of these numbers. So let's do this. And so for our objective function d, I propose that this here should be an acceptable solution. If not, these here, because all of these are the same, but this one's pretty clean. Let's see if they like that. If they don't, maybe you can give them that one or that one. It just depends on what is desired. Now, as for the interval of interest, that has to do with the variable that is being used, in this case, x. What are the limitations of x? How small to how big can x be? Well, let's see. Based on the map and how things are positioned, we can sort of trust the scale of things. X has to be positive because point P is in quadrant 1. And in quadrant 1, x coordinates are positive. So you know that x is greater than 0. But is there something that x is smaller than? I would say, again, based on the position of things, that since 74 is way out here, then the x coordinate of point P has to be smaller than 74, because really the x coordinate of point P is whatever this little gap is, which is way before 74. So x has to be bigger than 0, but at the same time, x has to be less than 74. I know that x has to be bigger than 0 and less than 74, but is there something in between that x cannot be? Some number between here and here that it's forbidden to be? To make that decision, look at your objective function. Here we have a square root with x's. That's dangerous because you might be accidentally square rooting something that's negative. We're not trying to square root negatives. So what you have to do is take the stuff inside of the square root, which is this here, that, and you have to ensure that this quantity is greater than 0. You don't even want it to equal 0 because if this is 0, then square root 0 is 0 and all of this disappears. So this content, this stuff there, make sure that it's positive. So now we have to solve this inequality. And how can you solve an inequality? What you can do is find the zeros of that function by letting it equal 0. Let's solve this equation by doing the quadratic formula. If you go quadratic formula, you're going to discover that in here, inside of the square root, you have a number that's negative, which means that this equation here has no real solution, which means that this expression is always going to be greater than 0. In this case, this is always going to be positive. So what I'm saying is that there is no value of x in here that is forbidden. X can be anything in here. It's going to work out as long as it's between 0 and 74. So our interval of interest, x has to be something between 0 and 74. Now to finish this problem, we have to find the actual coordinates of point P. And to find the coordinates of point P, we have to discover what x is. And recall what we're trying to do. We're trying to minimize this distance. Minimize it. Make this distance as small as possible. So minimize means a derivative. The derivative of d. So let's find the derivative of d up here. So d prime equals. Now you might think that this is a product rule, but it's not because this is a constant. This is just a number. If this had variables, yeah, it'd be product rule. This is just a constant, so that constant goes along for the ride. And really, we just have to take the derivative of this. So this is a square root. So the derivative of a square root, recall that that is the same as this stuff to the power of 1/2. So the derivative would be 1/2 in the front. Keep the stuff inside the same. And then you subtract 1 from 1/2 to get negative 1/2. But then you immediately multiply by the derivative of the stuff inside of the parentheses, which is 2x minus 4. Let's clean this up a little bit. So here is our first derivative, and I kept the 37, the square root 37 up there. 1/2 I left it up there, and I have that here. This came to the bottom because the power was negative, so it became positive in the bottom. And instead of exponent 1/2, I just did a square root. Now let's distribute the 1/2 to these guys there. So this is our first derivative, and that's really as clean as it gets. Now let's find the critical numbers by setting the top and bottom independently equal to 0. So I let the top equal 0, and I got 2. So 2 is a critical number of D. And then I let the bottom equal 0. I squared both sides. That's how I got rid of the square root. But then recall that this equation has no real solution because we did that earlier in the video with quadratic formula. So the only critical number here is 2. It's the only critical number we have. If you go to a sign chart for D prime, you make a cut at 2, it's the only critical number. Pick test values that are before and after 2, like 1 and 3. If you take 1 and plug it into the first derivative here, you will get back a number that is negative. If you plug in 3 into the first derivative for all the x's, you'll get back a number that's positive. Since the first derivative goes from negative to positive, we have tangents that go from down to up, which means that on the graph of D, we have a low point called the minimum. So all of this magic works when x is 2. That's what we take away from this. X has to be 2. This x has to be 2. And that's good because we're pretty much done. Go back to the model. This x has to be 2. And the y coordinate is 6 times x, which is 12. So when 212, which is on this line, point P is there, this is the shortest distance between these two objects. So that takes care of the next point. And then the last point is what it says, what is the least distance? So to do that, take 2, which is x, and plug it into the distance formula right here. So take 2, which is x, and drop it there and there. And that minimum distance would be exactly 12 square root 37. But if we round to the nearest tenth on our calculators, it should be about 73 units.